In section 1.1, we study inductive reasoning, which goes from the specific to the general, and deductive reasoning, which goes from the general to the specific. Often, as an example of inductive reasoning, you're given a pattern and asked to find the idea behind the pattern. In this particular problem, I have a feeling that most of you would see pretty quickly that we have the squares, 1 squared and 2 squared and 3 squared and 4 squared and 5 squared and so forth. And so when you look at these specific numbers 1, 4, 9, 16, and 25 and you figure out what's going on, you figure out that they're the squares, then that is an example of inductive reasoning. So usually books and teachers call this inductive reasoning. But then they often go on and say, use the idea to find the next few numbers. And once you use that idea that these are perfect squares, then you're using an idea to find specific numbers. Like you're using the idea of squares to find 36 and to find 49 and to find 64. And when you're using the general idea of squares to find some specific elements, that's actually deductive reasoning. So in this problem where you're filling in the next 3 numbers, you're doing both. You're doing inductive and deductive. And in our world, often they're mixed together. There are a couple things I'd like you to notice about this particular pattern, if you haven't already noticed them. And that is, for instance, that these first 2 squares are 3 apart, and the next ones are 5 apart, and then 7 apart, and then 9 apart, and so on and so forth, seemingly forever. That's kind of an interesting pattern in and of itself. And a second pattern is if you number these squares with their square roots. If you pick any one of these top numbers and multiply by 2 and add 1, look what happens. If you take this and multiply it by 2 and add 1, you get 11, and 25 plus 11 is 36. If you take this number and multiply it by 2, that's 12, and add 1, that's 13. 36 plus 13, excuse me. Touched the wrong button. It's a little easy to do on this tablet. So you can figure out how to go to the next number by multiplying these by 2 and adding 1. And to go to the previous number, you can multiply by 2 and subtract 1. So for instance, 4 times 2 is 8, take away 1 is 7, and you get back down to 7. So there's all different ways of looking at this particular pattern. Let's look at another pattern. So inductive reasoning asks us to go from these specific numbers to a general idea. And most people don't get to the general idea right away. Instead, they see that these are plus 3s. So 1 plus 3 is 4, plus 3 is 7, plus 3 is 10, plus 3 is 13. And so without thinking about it, they add 3 and get 16 and so forth and so on. And they get right numbers and they feel like they understood. But that's maybe not the best way to approach this. It's a way, it's a good way, but it's maybe not the best. There's many other things to find here. So, for instance, let's go ahead and do that so that we can, answer the question. But what if somebody says, okay, this is the first number, this is the second, third, fourth, fifth. We found the 6th, 7th, and 8th. But what if we want to find the 2000th number? Do we really want to add 3 a whole bunch of times, or do we want to have to calculate it? And the answer is probably no. So what else could we do? What else could we think about? Well, there's a couple ways to think about this. One is to think about these, for instance, let's give these numbers a name. Let's call these the n numbers. So n is 1, n is 2, n is 3, and n is 4. And so on and so forth, the natural numbers. And then I'd like you to think about this, 3n minus 2. This is an n number of 4. What is 3n minus 2? Isn't it 10? This is the number n equals 7. What is 3n minus 2? Isn't it 19? So this little generalization tells us a whole lot. If you want the 2000th number in this pattern of numbers, then you could put a 2000 in there and get 6000 take away 2, which is 5998. This is a pretty spiffy idea. It works pretty well. Is it necessary for you to know it yet? Maybe, maybe not. You could probably get these three answers without knowing anything about it. Let's take an excursion into the end of our course. There's another thing about these numbers, 1, 4, 7, 10, 13. If you divide any one of these by numbers by 3, if you divide by 3, the remainder is 1. These are the only positive numbers, the numbers in this list, where the remainder is 1. That's kind of strange. It's kind of weird. And we're going to use that at the end of our course. Let's go on to another pattern. I hope many of you would see that these are the perfect cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed. So the next one will be 5 times 5 times 5, and 6 times 6 times 6, and 7 times 7 times 7, and off we go. If we put our end numbers down just to give us a handle on, this is the fourth number, this 64, and this is the third number, the 27. Is there anything else we can do with these? Well, there's lots of things, but I'd like to show you something. So let's do this 1, which is 1 cubed, and so we're going to have 1, and we're going to have 1, and then we're going to have 1 plus 8, and then we're going to have 1 plus 8 plus 27, and so on and so forth. And over here, I'm going to square the 1 for no good reason. Then I'm going to add 1 and 2 and square that, and I'm going to add 1 plus 2 plus 3 and square that. And so if you continue this pattern, these are always equal. So the sum of the first n cubes equals the square of the sum of the first n numbers. So 1 plus 2, 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed equals the same thing as 1 plus 2 plus 3 plus ... plus n squared. And that is kind of an interesting formula. So you can see that these numbers have lots and lots of hidden depth and meaning, and some people feel hidden beauty. So maybe we think in this pattern that we can get the Fibonacci kind of idea. So 1 plus 2 is 3, and 2 plus 3 is it's 5, not 6, and 3 plus 6 is 9, not 11. But what happens if you add the first three numbers? 1 plus 2 plus 3 gives us the 6. 2 plus 3 plus 6 gives us the 11. 3 plus 6 plus 11 gives us the 20. 6 plus 11 plus 20 gives us the 37. And so if we were asked to find the next number, or the next three numbers, we could add. So you have 11 plus 20, that's 31, plus 38, 37, that would be 68, and so forth. And so this pattern is pretty sophisticated. To try to analyze it with n's would take us beyond the scope of our class. So there's hidden beauty here, but for now we're going to pass on that hidden beauty. So here's another example of inductive reasoning. We're asked to pick a number, so I'll pick a number 7. We're asked to multiply it by 2, so I'll have 14. We're supposed to add 6 to that product of 14, so we add 6 and we get 20. We're supposed to divide that by 2, we get 10. We're supposed to subtract 3. And then we're usually asked a question like, did you notice anything? And maybe you do, maybe you don't, but I tended to notice that there was a 7 at the beginning. That's the number I picked, and there was a 7 at the end. That's a number that I picked. So I guess the idea is we should try it again and see what happens. And so let's pick 3. We multiply it by 2, we get 6. We add 6, we get 12. We divide the 12 by 2, and we get 6. And we subtract 3 from that division, that quotient, and we get 3. And once again, So the idea behind calling this inductive reasoning is that we've used some examples like 7 and 3, and we're getting this idea, hey, this happens a lot. Maybe it happens all the time. So that's our idea. We think it happens all the time. Now, a separate thing is to try to prove that it happens all the time. We might try a fraction, we might try a decimal, we might try a negative number, we might try the square root of 2 or pi. There's all kinds of things we could try. But let's try a proof. So let's let n represent our choice, and n can be any kind of number we want. So then we're going to multiply it by 2. That'll give us 2n. We're going to add 6 to the product. That's going to give us 2n plus 6. We're going to divide that by 2. That gives us 2n plus 6, the whole thing divided by 2. But that's 2n divided by 2 plus 6 divided by 2. That is n plus 3. So on this next to last step, we have n plus 3, and now we're supposed to subtract 3. n plus 3 minus 3 is n. And so we've shown that if you start with a number n, any number n, you're going to end up with a number n by using some algebra. That's all. That's kind of interesting. There's a lot to learn if you're learning about proofs of things, but one idea is pretty basic and pretty important. So let's take a look at a general statement that some of you may find offensive. I don't know. Notice I'm not declaring that this is true or false. So there's a general statement. All males are stupid. Now the question is, how could we prove that that is true? And the way to prove that that is true is to prove that every single male that's ever existed, whether they're human or animal, or whether they're dead and ancient, or whether they're present, I don't know about the future males, but is to prove that every single one of them is stupid, without exception. And once you've proven that every single one of them is stupid, without exception, then you've wasted a great deal of time, and you can then make this statement, and it is a true statement. Well, that's pretty hard to do. Nobody can really do that. So instead, let's talk about how we could prove that this is a false statement. What would it take to prove that it was false? And the answer is it would take one male who was not stupid. Just one. And then that proves that this, as a general statement, is wrong, that there's an exception. That exception is called a counterexample. You can prove something is false with one counterexample. You can't prove something is true with one example, but you can prove it's false with one counterexample. So let's use this in the next problem. So what about the statement, the sum of any two odd numbers is divisible by 4, followed with this very convincing looking argument. 1 plus 3 is 4, 3 plus 5 is 8, which is divisible by 4, 5 plus 7 is 12, divisible by 4, etc., etc. Can you think of a counterexample? What about the two numbers, odd numbers 1 plus 5? 1 plus 5 is 6. 6 is not divisible by 4 because there's a remainder of 2. So this one counterexample, and there are many other counterexamples, proves that this statement is false. Just one counterexample. Doesn't matter how many examples work out. One counterexample proves it's false. Notice if this had said the sum of any two consecutive odd numbers that are right in a row, is divisible by 4, then that would have been a true statement, and we could actually prove it towards the end of our course. This represents the first of the odd consecutive numbers. This represents the second one. When you add them, you get 4n, and 4 times n is divisible by 4. Done.